Good morning. We are going to have two back-to-back sessions for healthcare robotics. You have seen many great presentations at GTC, a lot of them about physical AI. Now we are going to take physical AI and tell you what the leading research and companies are doing, bringing it to the most difficult challenge and the most difficult test of physical AI, which is healthcare. So I'll kick off by just repeating some of the slides that you have seen, right? The opportunity is massive. The need is massive. Every person in this room either is a patient or related to a patient. The healthcare system has a crisis of demand and supply, and robotics, in our hypothesis, can help immensely. So as you listen to the speakers across different use cases of healthcare, you're going to see how physical AI, how these horizontal technologies are helping already bring in a lot of innovative solutions to make things faster, more efficient, and more accurate. But for physical AI, everybody knows the main challenge is data, right? And this slide is by design supposed to be boring. 4 boxes. In an ideal case scenario, you're going to have the data that is curated, annotated, you know what you're looking at, it is searchable, you find the distribution of the data that you have, you understand what you don't have enough of or you don't have at all, and then you go and bridge that data gap, those long-tail data, and use synthetic data generation and simulation to bridge the gap. Ultimately, you go, use the data to train a model and deploy, and everybody's happy. As simple as it looks, every single one of these boxes needs many PhD students to work manually to make it really happen for a proof of life. The data curation and annotation is very time-consuming and inconsistent. Between 2 even residency departments, the outcome is totally different. When it comes to the synthetic data generation and simulation, for many years, researchers tried to solve the challenges of healthcare robotics when it comes to surgical robots, clinical robots. There are gaps. And ultimately, when it comes to training the models, right? We are dealing with a dynamic environment in healthcare. Whether you're looking at the anatomy or hospital halls, everything changes in every second. There is no prescribed path. So you need generalizable models, right? So across this presentation, from the first presenter to the last, you're going to see the new innovations across each of these boxes. And then you're going to hopefully connect the dots how these technologies are going to help get us where we want to go. Basically, 3 fundamental shifts that we see in other industries that we are bringing into healthcare robotics. The word foundation models that create physically accurate data without solving the physics, right? That could be our kind of a solution to address the fidelity of simulation, right? Generative physics. The second bucket are those foundation models that you have seen many of them coming out these days from many of our partners and NVIDIA itself. Models like Groot, Alpamayo, that reasons when you go and drive, and it tells you why I'm doing what I'm doing, which is very important when you are thinking about healthcare applications, right? Explainability. And the last part is what is happening today with accelerating simulation and increasing its fidelity. These 3 pillars and the shifts in technology is unlocking physical AI in other domains, and we think is going to do the same for physical AI in healthcare robotics, and our task is to bring those and make them real. So today, when you look at it, you are going to deal with a lot of models that are going to be open sourced, right? And we are on the leading kind of edge for these type of models. But your development starts by taking those models and adding your own data. If you have real world data, great. If you don't, you have 2 other paths. Generate data, like models like Cosmos that we talked about, to generate data, and you're going to hear from our partners that are doing that. Or simulate data, solve the partial differential equations, the traditional way, first principle way. Now you have a good, healthy mix of 3 sources of data, post-train those open models, deploy, test. You can test in silico, which is going to be much faster in simulation or inward foundation model, and the flywheel keeps going on. It is all about the data flywheel. And you see many of the leading companies on this page. The same pipeline applies for non-clinical robots, hospital automation. And with that, without further ado, I want to introduce Filippo to start from the first couple of boxes of that boring slide, and then we go from there.
Beautiful. Well, thank you, Mustafa, for having me here. My name is Filippo Fulcori. I am a surgeon. I am the program director for the Robotics Fellowship at Lenox Hill and Northwell Health, the largest healthcare provider in Northeast United States. So what we do is we take board-certified surgeons and we tweak their skills, and we get them ready to go out there and practice in the real world. I also lead a laboratory that does research in predictive analytics for surgery, so looks into the performance of a surgeon as a whole and comes up with ways and models in order to improve the performance of the surgeon. We have seen an incredible innovation in the surgical environment over the past 30 years. For thousands of years, people used to do surgery in the open fashion. And then 30 years ago, we started doing surgery with like small cannulas and laparoscopy. And then the real revolution came with the robot. Now the robot has more than 30% of the share market of the minimally invasive surgical space. And the robot allows you to collect all of the data. We're really only leveraging a minority of the data that is coming out of the robot. And we're all really working hard in order to understand the data that comes out of the robot and to make it actionable so that we can bring out to the field better surgeons. But there are a lot of challenges dealing with healthcare data. First and foremost, it's really hard to get data out of hospitals because of medical legal problems. Then it's very hard to curate the data. Just surgeons and all of those clinical people that need to give you the annotations are just really hard to pin down. And thanks to video language models these days, like we can embed the video language models in our pipelines, and we can actually really improve and cut down dramatically the time that is required to annotate these data sets. And then, whenever all data is not just the same, right? Like when you have a video of a surgical procedure, the high impactful moments are going to be 2 or 3% when you're going to have a bleed, when you're going to have an inadvertent injury of a certain structure. And also, we have a huge lack of ontologies and taxonomies in surgery. We just never asked ourselves that problem. And so we're working in order to fix that problem as well. And we are also working really hard in order to enable going from real data into simulation data, and together with Cosmos, the Cosmos product, we are going to be able to create better simulations that really take from the real world and allow us to train a better generation of surgeons and then potentially enable autonomous sections and so on. Because the final and the ultimate goal that we have here is for a model to have full surgical scene understanding. So for a model to understand exactly what is going on in the screen. And NVIDIA is helping us out by doing that, and we're taking a page off the playbook that they use in autonomous vehicles. So we're using the same kind of pipeline and with some of their products, including Cosmos Search and Surgical Robotics. If you're a developer, if you're working on creating models around surgical performance, you can search a specific event, or you can search a specific procedure, and you can use that data in order to leverage and create better models that are specifically tailored to that event as well. And as I was telling you, we've been doing a lot of work around surgical ontologies. I mean, there's no way around this. In order to create surgical ontologies for procedures, you need to get a lot of surgeons under the same roof, surgeons that are both smart and savvy about ontologies and the ultimate use case for computer vision, modeling, kinematics, and autonomous surgery. So this is what we did a couple months ago. We got a lot of our members from SAGES together, and we created an ontology that looks into the surgical gestures. And surgical gestures are key because basically all the surgical gesture is what really powers video language action models and so on. A month later, we were able to apply the surgical gesture framework into the OpenH data set, and this was a great honor. Obviously, whenever you're annotating these surgical procedures, so for example, in the top left videos, you're going to see two things. You're going to see certain anatomical structure being annotated because those are the places in the human body where you have large large vessels. And if you get down there, you could be creating like even some lethal injuries. And also like the target anatomy for repairing a hernia, for example. So you see the ligament over there that it's being annotated. And that's kind of the landmark for us to perform a high quality surgery and put in a mesh so that the patient doesn't have a recurrence of his own hernia. And talking about simulation, I'm a huge fan of simulation. This is like a state-of-the-art product. It's SimNow 2 from Intuitive Surgical, and this is me at Italian Tech Week a couple of months ago. I enjoy like talking to audiences of engineers, and I was simulating, in real time live. And this is a great product, but it's still like a simulation where every pixel is rendered pixel by pixel. And we really do think that we can do better than that. And together with Sean Hoover and Nigel and Kai, we're really trying to bring to life their Cosmos Age real-time simulated environment. So this is a different approach to simulation. Instead of rendering everything pixel by pixel, the idea is that we basically create a ground truth given by the first frame of the surgical operation, and then we use the kinematic data in order to simulate the interaction with the tissue. And we've created a whole suite of models, including Gaussian models, to simulate the interactions between the tissue and the tool. And we're working hard to bring this to production, and so that all of our surgical trainees can have a better environment where to train and learn. Because, like, believe it or not, simulation is hopefully underutilized in surgical training. So the people that are actually operating on people, they sit down at a console with me, and they do actually learn how to operate on real humans. And this is not fair, it's not ethical, and that's why we're trying to really work hard to make this better. And last but not least, I just wanted to show you this video of an autonomous robot that was pre-trained with OpenH and was trained with Groot. I'm not going to talk about the technicalities that it's going to be for Axel, but in the upper left corner, you see a surgical intern, so a first-year surgical resident suturing. Suturing is actually one of the most complex things that you can do with a robot, and you see how much the surgical intern is hesitating. And this was amazing work done by Axel and the NVIDIA team, and using video language action models, which reinforces the fact that gesture ontologies and gesture words are really important. The model and the robot was able to throw a stitch and tie a knot. And with that, I wanted to thank all of my team for the incredible work that they're doing in advancing our surgical knowledge. Thank you.
Thank you, Mustafa, for inviting me. Really thrilled to be here today and tell you about our work on autonomous robotic surgery. Wanted to start with quick disclosure. In addition to being an associate professor at Johns Hopkins, we recently founded Semaphore Surgical, where I'm the chief robot officer. Here. We are showing this rising caseload, so this upcoming healthcare crisis where we have projected in the next 10 years a doubling of the caseload. So we as engineers really need to provide technical help to cope with this rising caseload. Manual and teleoperated robotic-assisted procedures, of course, heavily depend on the experience and the skill of the operating surgeon. Our vision is to augment critical parts of this manual-operated surgery with increasing levels of autonomy. This could reduce complications, democratize access to expert surgery, and help with that rising caseload. Traditionally, we have solved this problem with a model-based approach. So we have published a paper in Science Robotics 2022 where we first track tissue in 3D, then planned. We had to develop our own custom suturing tool, custom camera system. And while this is predictable, we definitely hit a ceiling on performance, about 60% stitch-to-stitch success rate. And it really doesn't scale to new procedures. So what is super exciting about these learning-based methods, and in particular imitation learning-based methods, that we can build one framework and then add more data and learn new techniques and new skills on the fly and get better and better. So we started this. We use for the hardware the DaVinci Research Kit. We added a wrist camera and started with tackling some fundamental surgical tasks like lifting tissue, needle pickup, and handover and knot tying. High level, really, relatively simple. We get expert robot demonstrations. We capture the video and the associated kinematics, and then learn and train, transformer models to, produce the right action, giving the right video input. And with just a few hundred expert demonstrations, we were able to show that we can perform some of these expert procedures with high fidelity. So on the left you see knot tying, on the middle 100% success rate, needle pickup and handover, and then lifting tissue, the simplest task, 100% success rate. But what is super nice, this is not sequentially programmed, so it's really robust to disturbances. So here we knock the suture thread out of the grasp, and it automatically repairs itself and completes the task. But this is all suture pad, and this is really small little surgical task, right? So how do we get it to the next level and perform, procedure level, phases of, robotic surgery? We've been digging into the cholecystectomy, taking out the gallbladder. We published this in Science Robotic last summer. We're focusing on this middle phase of clipping and cutting the bile duct and cystic artery. We obtained about 30 gallbladders in-house and repeated this clipping and cutting 20 times on each sample to get about 16 hours of gallbladder surgery data. Then we trained this hierarchical policy. So now we divided the whole phase of surgery into different subtasks, and first have a high-level language policy that looks at the history of the video and then finds out what is the phase of the surgery that we're currently doing and if there are any corrections needed. And that feeds into a language-conditioned, low-level policy that to then execute and find the associated kinematics. It's very nice to also intervene as a surgeon because the robot tells you what it wants to do next. So, really nice way to intervene. And here, an example video then in our study. Fully autonomous, did not require any intervention. You see some adjustments when it initially misses on the bile duct. And here a clip applier comes in, places 3 clips. Then we change into a scissor and autonomously cut the bile duct. And then the same on the right with the cystic artery. So really nice demonstration that this hierarchical framework can achieve high fidelity autonomous soft tissue surgery in this ex vivo porcine model. And here's a compilation of 8 consecutive study videos in our ex vivo model. We since deployed this framework, the SRT framework, on different robotic systems for different application. Top left, you see endoscopic guidance, and then for endoluminal guidance under X-ray. You see the suture bot that we published in NeurOps for end-to-end suturing. On the bottom left is for tracheal tumor resection, and bottom right is an example for partial nephrectomy, so cutting out a portion of a kidney cancer. So all these examples are in-house data set and policies that we trained with in-house, bespoke, policies. So really to take this to the next level, super excited to have collaborated with NVIDIA and so many partners to create a much larger data set so we can, create much more robust, policies and really tackle, cross-embodiment tasks and more, more applications. So we collected over 150,000 trajectories with kinematics. That's the largest surgical robotic data set. Publishers put it out on Monday and already have 1,000 downloads of the 1 terabyte of data. So I think it really creates a lot of excitement in our community. What can we do with it? We can train Groot to perform suturing. So this is trained on the full OpenAge data set and then fine-tuned on SutureBot. And here's an example of end-to-end suturing. So super exciting early results. Hopefully we'll follow this up with a paper in the next months with a more detailed study. But already in this initial few weeks of testing, we showed that we can outperform the state of the art in suturing with this Groot Age model. And what is also super exciting that it doesn't require a lot less suture data to get proficient. So on only 33% of the data set, we already achieve really high performance. Another collaboration is with NVIDIA on Cosmos, where we trained a world model trained on OpenAge. And you can see always the video pairs. The left is the original video. The right one is the AI-generated one. So super exciting that we can make this so realistic, and that helps us in policy testing. Where do I see the future of autonomous surgery? It's going to take a little while before procedure-level autonomy, becomes, a product. But I think these autonomous functions in laparoscopic surgery will come over the next few years. Super exciting that Moon Surgical already has the, camera control. Other lower-hanging fruits that are a little less risky would be suction, holding, and tissue traction, and port placement. With that, let me thank my team and all the great collaborators, and thank you so much for your attention.
All right, hello everyone. Mustafa J, thanks for having me here to talk a little bit about how we're looking to close the data gap to enable physical AI on Maestro. And so thanks Axel also for the shout out on our Scope Pilot feature. So for those of you who aren't familiar with Maestro, I just want to quickly introduce it. It's a 2-armed cart-based system that collects to off-the-shelf laparoscopic instrumentation. And we believe that this is enabling a new category of minimally invasive surgery, one that allows for more procedures with fewer resources, enhances procedure consistency for increased patient safety and OR staff quality of life. And crucially for this conference and audience, we're equipping the OR with a closed-loop feedback mechanism to deliver AI-based continuous improvements. And we're available in the US and the EU, and we have a broad indication for holding and positioning laparoscopic instruments. So the system itself, at its heart, is a collaborative surgical robot. And so the user is able to grab or hold of his or her tools and move them anywhere in the workspace. When they let go of the tools, they'll be locked in place. And so the system sort of infers the intent of the user. In this particular part of the clip here, you can see a setup joint being repositioned. And this is key to the sort of later part of my talk, where I'm talking about how we configure the system at the beginning of the surgery is a problem statement that we're trying to solve or make more efficient, and simulation can really help. We can also port hop, as you see here, moving from one port to another without any re-registration. And as Axel just alluded to, the first sort of advanced feature we've deployed is, we call it Scope Pilot, where here, as the surgeon is moving the instrument manually with their right hand, the camera is automatically following it. So we're giving the surgeon the ability to control 3 instruments with just 2 hands. Maestro adapts to any laparoscopy, so I'm showing you here just 4 different surgeries. And the reason for showing this slide is that you'll notice that the arm configurations in every surgery here is very different. And so one of the things that we're trying to do to make surgery more efficient is allow them to set up the system quicker. We have done over, at this point, nearly 3,000 procedures, but you'll appreciate different rooms, different setups, different beds, different surgeon heights. very much each case is slightly different, and you either do thousands and thousands more procedures to optimize this, or you simulate to try and make things faster. And that's exactly what we're doing, and I'll talk about in a moment. Before jumping to that, I just want to touch on the fact that Maestro was designed from the beginning as an edge compute powerhouse to be at the bedside. So moving around this graphic from left to right, we pull in the laparoscopic video feed so we can see inside the patient. We have two 3D depth cameras doing RGB and D imaging on both on the top of the, what we call this, the lighthouse, and also down below, lower in the system, so we can see outside the patient. And I'll be referring to this lighthouse camera a little bit later, so just want to draw your attention to it. The robot arms themselves obviously are sensors, in our case high-resolution force sensors. The system is connected, outbound only at this point, but it's connected to Wi-Fi or 5G. And all of that is interfaced to the IGX Orin with an A6000 GPU and an Agile capture card. So that's the product as it is today, but obviously this is a session on simulation, so I do want to touch on how we are using simulation to close the data gap. And our first target application is optimized arm deployment. And I love the SutureBot from Axel, but in a regulated environment, there's a crawl, walk, run element to this. And the first place that we're targeting is something that is a lower patient risk. It is set up. I fully believe we're going to keep moving through the risk profile to be more and more advanced things, as Axel touched on. But where we're starting is in optimized deployment. And this is not currently a feature, but I wanted to share as to how we're thinking about the problem and what we're doing. So if you take the three computer concept on the top left, we're simulating in Isaac for healthcare with the Maestro embedded within the simulation environment. We're then generating synthetic and using real world data and training to simulate lots and lots of different configurations. Again, we don't have to get to the point where we've done 50,000 surgeries to simulate 50,000 surgeries. And thankfully we now have the tools to do this. And then lastly, in the bottom, we have the deploy side where we have the IGX at the bedside. And this video clip just shows an example how the arms might deploy. So going through this, first up you have the simulation. And what's cool about this simulation is that it's running our full software stack. So that's our user interface. And you can touch on the user interface as if you were a user, and the system, is that not playing? No, it is not. Okay, no worries. Let me go back up. But what you would see here is that as you go through the user interface, you touch on the GUI, the arms will deploy, the system will move, and you're basically getting a full simulation within it. But you'll appreciate we're able to move the system relative to the bed, the angle, the height of the bed, the color of the drape, all of the different configurations that we would see in a clinical setting, and that it's been very powerful. It is a great debug tool if you're looking for debug tools as well, because the software stack is integrated, and we're using it to render different configurations. But there is a need to enrich your data set. And so what we're doing here is we're taking real world video from that top camera I referred to, and we're generating synthetic versions of that video using Cosmos Transfer. So the video on the top is a real video as recorded, but the lower one is a synthetic video that's been generated, fine-tuned Cosmos Transfer. And so things that are different, there's no blood on the patient's skin, the skin has changed, the profile of the drape is different, the light cable is a different illumination. And so this way we're able to generate different clinical scenarios without having to actually do the procedures themselves. We're also going the other way, where we're taking the Isaac Sim, visualization from that top camera, and applying Cosmos Transfer to generate realistic, or the goal is to generate realistic imagery. So we, again, don't have to create those images even from a real setting. But what you'll see, if you look closely at the hands, at that top image, there's actually Cosmos Transfer put hands on the robot. Now, our robot doesn't have hands, but I guess that's where its background is coming from, the World Foundational Model. And so there is a need to fine-tune that with real-world data. So this is still a work in progress. It's definitely not solved yet. The best result we've gotten yet is in the lower video. It has improved the drape, some of the elements of the skin, but as I said, it still has some way to go. But I do hope to be back here next year and showing results from that. We then take the training data sets, the synthetic and the real, and we start to apply training. And so there's two, or apply them to training. There's two different sort of problem statements here. One is on the left, you've got the global environment where you've got the bed, the patient, the robot. That's one set we're doing. And the other side of it is the actual perspective from the camera, because you need to teach the system to be able to perceive the scene and then decide what to do next. And our goal here is obviously to identify an optimum pose for a given clinical scenario. From a deploy perspective, as I said, regulated environment, we do have to take things slowly. What we'll start with is a workspace optimization button in our GUI. And so if the system is able to perceive a scene that meets certain criteria and has identified an appropriate pose, this button will appear and you'll press it and the system would then deploy to that location. But where we're going next, and as Axel and Filippo touched on, is training vision language action models with this data sets and deploying them directly on Maestro. And so we have just recently a trained version on GR00T N1.6, and Sean told me yesterday it's already obsolete, so we have to talk to the guys about that. And things are moving pretty fast, but it's exciting to think of what we will be able to do. And again, I hope I'm back here next year to talk about the results on that. So lastly, where are we going? And I listed it as VLA-driven capabilities, and intentionally slightly vague there because I think there is definitely a hierarchy of tasks that we'll tackle based off the risk to the patient and the surgeon. But we do have this data set of cadaver data where we can do very controlled experiments, synthetic data, real-world data, curating that in the robot format as the OpenH initiative is harmonized around. We're training both. So we do contribute to the OpenH data set as well in GR00T N1.6. And then lastly, the evaluation and deployment. And draw your attention to that image on the left of the eval and deploys. I took it from a presentation I gave a couple of weeks ago at ORSI and at the ORSI Surgical AI Day, and wanted to call out that in a regulated environment, we will absolutely need to consider the safety and system architecture to deploy these things. And the AI will sit in the middle of it, but there will be nested loops that you're making sure that the system is doing exactly what it needs to do to be safe for the surgeon and the patient. And that's it. Thank you very much.
Hi, hello everybody. I'm Yossi, CEO and founder of LEM Surgical. LEM is a Swiss company. Our software director was supposed to be here today. He hurt his back, couldn't sustain the flight from Switzerland, so you're stuck with me. We're FDA cleared, and small disclaimer, some of the things that I will show are future development. This is our mission, reason we wake up in the morning. As you can see where we are now, so a red bar is elderly population in the US above the age of 65. The blue bar is available surgeons per population. So as it appears in 2025, we're okay, only a small number to remember. Today, 40% of US orthopedic surgeons are above the age of 60. So take it 4 or 5 years down the road, and then you see the perfect storm coming a few years from now. There will not be enough surgeons, in our case, orthopedic surgeons, to treat the elderly population. And something needs to be done. This session is about physical AI. Something needs to be done which is not incremental software improvement. Something needs to be done in the physical world to really accommodate for this coming problem. I think also Mustafa mentioned this, and many are talking about it. This is quick. I think all of the sessions until now were in the soft tissue area, and really the last 2 decades, the soft tissue robotics were the most dominant. We are in the hard tissue robotics, hard tissue, spine, long bones, joints. And there in the hard tissue, the robotic architecture is very different from what you're accustomed to see. In soft tissue robotics is most of the time remote manipulation. Moon is an interesting, I don't know to call it an interesting case, but in the large form factor of surgical robotics in soft tissue, it's 2 to 4 robotic arms. The surgeon is not even touching the patient, sitting in a console, and it's a remote manipulation. It's a teleoperated procedure. In hard tissue, it's a bit different. Bigger, stronger robotic arms, and the most dominant form factor, and there's only few examples here, is usually it's one robotic arm coming from the bedside, merged with what is called a navigation camera, most of the time an infrared camera. And the basic idea is there, it's a concept invented 30 years ago. The idea is one bone marker attached to the bony anatomy, one bone marker in the end effector of the robot, and what you see here is this, you don't really see it on your screen, never mind, you see this stationary camera. It's usually an infrared camera, so this camera looks at these markers and determine where the end effector, the tip of the robot, is in relation to the bone. And then this robot can assist the surgeon in hard tissue, usually is to drill, to apply saw, to cut planes. And this is how it is done today. The equivalent for this is if I would tell you, imagine yourself trying to hammer a nail to the wall with one hand, because this is what you have today, one robotic arm, and you're trying to hammer a nail to the wall or to tie your shoelaces, never mind the analogy. One robotic arm is very limiting. It's a very limiting architecture. That is why, while you can see today intuitive and soft tissue robotics really very proliferated significantly, in hard tissue robotics it's a different picture, because these robots are relatively limited, can do only simple tasks. So what do we do in LEM? We bring a first of its kind upper torso humanoid architecture, meaning two robotic arms synchronized with a third arm, which is the vision, and then you can have the human architecture that you are so familiar with and use it every day without noticing it. You're something so simple like to tie your shoelaces. Again, try to do it with one hand. And this architecture is missing in hard tissue, so two operating arms, a dynamic vision that is synchronized with the arms. Don't have enough time to explain why is it important. One of the key elements is instrument and implant agnostic. I mean, what does it mean? The ability to operate any tool, and not only proprietary tool that we know. The equivalent is if I give you 30 different markers or pens, you can operate all of them. No problem at all. You take it, and within a second, you calibrate it and you operate it. In robotics, hard tissue robotics, this capability doesn't exist. You can operate with the $1 million robot that you bought only my proprietary implants or instruments. And this is a very limiting thing, and we are also doing this, where the idea is, last bullet, we want to have the pathway towards supervised autonomous surgery. We want to raise the bar so the robot can do more sophisticated tasks and to automate parts of the procedure. How does it look? So let me play this. So now you have this upper torso humanoid architecture, the two operating arms. So you have the two arms. One, in this case that you see, one can stabilize a specific bone, monitor it, have plurality of cameras and sensors. So while the other arm doing what you see here as a bone milling, the specific bony element is controlled, stabilized, and then you can have predictable results. This is the reason why current robotics cannot do it. You need to have predictable results, and that's what we're doing. Let me jump this forward. Now, where's the challenge, and where we are cooperating with Mustafa and the guys in NVIDIA? One of the things that at least occurred to me at some point, that a simple robot can do simple tasks, but also can do simple mistakes. It's relatively easy for the surgeon to say, you have one arm, come, stand here, do this. Very simple. Now you have this sophisticated robot that can do multiple things. And the equivalent, as a father to small girls, the equivalent, you give your kids a fork and knife, and you put it in their hands, you say, eat nicely. What does it mean? So you say, no. So you tell them, this is how you hold the fork, this is how you hold the knife, and eat your pasta. Okay, so they learn to do it, but now it's not pasta, now it's rice. So it's a complete different action, and now it's different food. And I'm not even talking about more complicated things than a fork and knife. So this training is a challenge, and it's an iterative process that needs to be done. And again, I go back to our situation. When you have this three-arm system and you want to deploy it in the field, this system needs to have a basic training of how to behave, how to move. And one thing that differentiates hard tissue significantly from soft tissue is the fact that it is a collaborative robot. There is people always there, between 5 to 10 people working together with the robot. So I will do this part fast because I see I'm running out of time. So I will jump this forward. But the idea is you have this complicated or a very capable robot cooperating with several people around the table, and you need to train it. 1 second, sorry, I will skip this quickly. There you go. So one of the things that, at least in our list, we first to solve before we go to the clinical application and to the bone and to the tissue, how this robot can collaborate with the people around. There are people like the one that you see on the right, a sterile person. Okay, so the robot can come close, even touch it, but the other guy is non-sterile. You cannot come close to it when you're sterile. There are instruments, sharp instruments. Again, one thing very common to heart tissue surgery, orthopedic surgery, hundreds of different instruments, not your instruments, other vendors' instruments. So this robot needs to know how to collaborate with all these people going around him, the instruments that are involved always in the surgery, and then the clinical application. So with current decision matrix, we cannot, the number of variables, do the math is it's not scalable, this solution. And here, AI is something that we see with a high value, how to create what the guys can explain or explain better than me, to create this, and I will skip the flowchart, but to create this simulator, create this synthetic data, and now train the robot in a scalable way. So in the first time that we deploy it, and I'm finishing here, the first time that we deploy it in the OR, it has the basic ability, the basic knowledge of how to behave, so the surgeon and the surgical team can collaborate with it successfully. Thank you very much.
Just a couple of quick questions. If there is any, the amazing speakers are here. Jay is going to pass the microphone, and you guys can ask questions. Just 2 short questions, please, if there is any.
This is all. I'm Jonathan Strong. I'm actually a home and community-based provider up in Alaska. Are there any robotic stuff going on in home healthcare? Because that's where I'm at. But anything that you guys have heard of in home healthcare to help like elderly and disabled people in their own homes? Anything like that you've heard of?
Yes, there are companies that are working on those, yes. Across the board, you can think of like from even infection control to delivery within the hospitals and beyond, right? And then you can even think about exoskeleton type of robots that are going to help you, and that is not within the confinements of the hospital. But yes, there are robotic companies working on that, and the tools and the stack is the same, right? You still need data, you still need to train. One more question.
Hey there. I work with a lot of startup companies in leveraging the Jetson Thor platform. I'm curious on 2 ways. When I help out with smaller companies who don't have simulation data and are trying to leverage that to train models, are they able to access like the OpenH or different things to have a data set to work off of that's public? And then secondly, when you guys are using the Jetson for the multi-sensor input processing, is that running the full learning process on top of those as well, or do you have to have 2 machines communicating?
Two machines communicating, but that's a great question because our next session, and you see Jay here, please be seated or just take a quick break and come back. These are the same sessions back to back. We're going to go in depth about the runtime computer and kind of differentiating between what you need for the runtime versus what you would need in the training.
That's all the questions we have right now. What we're going to do is we're going to get these guys off, get the next speakers mic'd up. Everyone can kind of stand up, stretch their legs, and feel free to mix and mingle between sessions. And we'll see you back here at the top of the hour. Thank you so much.